Hello guys, nice to see you. Hi. Let's wait maybe 1 more minute, let people join the meeting. Okay. Hello guys again. See already more people. Nice to see you. And let us continue working. So last time we introduced electric field at the end of our previous online lecture. And we highlighted that there is a direct relationship between the electric field vector and electric field vector. Why it's not? Oh, now it's working. And Coulomb force. So summarizing this, let us consider some large positive electric charge, and let's call it Q, it's positive plus. Then we have some point in space, let's call it P, where we place a small test charge, and also positive, so it will be plus Q naught. So this small test charge we need in order not to disturb too much electric field around the source charge, which is large and predominantly defines the electric field in the nearest surrounding. So there is some distance from the source charge to the test charge, which is defined as R, and we have some unit vector which defines the direction of this radius vector R. So in this case, as we mentioned earlier, we have a definition of electric field. It will be directed in the same, like aligned in the same direction as the Coulomb force, like, or electric force, which is exerted on a positive charge. So in this case, we have two positive charges, and our test charge is also positive as a source charge. And that's why we have some repulsion between them. So the electric force will be directed from the source charge along the line which connects two charges. And by definition, our electric field vector will be aligned in the same direction as the electric force acting on the positive test charge, which is located in the given point P, where we want to determine electric field vector. So obviously, let's then maybe write again expression for the electric force, actually Coulomb law, between 2 point charges. So we have Coulomb constant, then we have charge of the source charge, then times probe test charge, divided by radius square of the distance between these two charges, and times the radius vector. In this case, according to the previously defined equation for the electric field vector, we can write that electric field vector is equal to, so we kind of normalize the electric force by the charge, like magnitude of the charge of the test charge. So will be KE. Here we have only source charge because we divide force by test charge Q naught, R square, R vector. So this is how we define the electric field vector. And obviously, if we have negative charge as a source charge, and at some distance we have positive test charge, then it will be attracted towards the, this is positive, towards the negative source charge. And according to the definition, so this is our electric force vector, electric field vector will be now also directed in opposite direction and will be aligned towards the source charge. So based on these examples, we can make a conclusion that, like so far, that electric field of a positive charge always is headed from the charge, and of the negative one, it's always directed towards the charge. So these key key questions you should keep in mind. So here we have a question in the chat that R vector, represents the direction. Sure, you are right. It's not the magnitude. Magnitude is just R, but R vector is a unit vector. So its magnitude is unity, and it is used only to define direction. It's something the same as, for instance, we have a system of coordinates. We have X and Y, and we operate with unit vectors I and unit vector J. So these unit vectors define the directions along respective coordinate axis. By the way, we will come to this point of using them quite soon. So, okay, let's go further. Another question which we need to address now is how to calculate, because usually we deal not just with single charge somewhere isolated from the universe, but usually we deal with some system of charges. And in that case, we also want to determine electric field vector in each given position in the space. So this is actually the main task of electrostatics, to calculate the electric field vector in the given point of space. And of course, there are many cases when there are many charges. In this case, we need to calculate electric field of each electric field vector in a given point. For instance, we have maybe let's consider a system of two charges. So let's have a system of coordinates x, y. Also, we have here I unit vector, j unit vector. And in this system of coordinates, we have two charges. Let's say a positive charge Q1 and another charge, let's say negative charge Q2. So let's say here is some point P where we want to determine the electric field vector. So obviously we have to do it step by step. We need to calculate electric field vector in point P created by charge Q1. Then separately we need to calculate electric field in vector in point P created by charge Q2. And then following this principle of superposition, which is valid for electrical field, we can, which states that electric fields of different charges do not interfere with each other, don't have any impact on each other's electric like capabilities of creating electric fields. We can just add as vectors these two electric field vectors and find the resultant vector of electric field in this given point. So let us try to do this for the example of this simple system of two electric charges. So let us start with charge 1. And we know that electric, from previous slide, electric field vector, let's call it 1, will be equal to Coulomb constant. And we have electric. So maybe let's go without vector here. Let's deal with absolute value, and then we will define where it will be oriented. So we have Coulomb constant, Q1, and take absolute value of it, and R1 squared. So this distance R1. This distance is R2. Okay, so we have equation for the magnitude of electric field, a vector. And here what we see, we know that electric field vector is oriented from the positively charged, positive charges. And it is aligned along the line which connects the charge and the point where this electric field vector is has to be determined. So we have this line, and that means that this electric field E1 is directed along axis X, because this line between which goes through the charge Q1 and point P is horizontal. It goes in parallel to axis X. So this is our E1 vector. So similar we can do for the, so maybe now let us define this mathematically. So how can we do it? Let's write E1 vector is equal. So we have two system of coordinates in this case, X and Y. What is the projection of vector E1 on axis X? So it's actually full length of this vector, its amplitude. So that's why we can write, because this vector E1 is parallel to axis X. So we can write KE times Q1 absolute value divided by R1 square times I vector, like unit vector along axis X. Then we need to have also projection of this vector on axis Y, because we have two coordinates. However, here, if we see, since it's parallel to axis X, projection of axis on axis Y is 0. So we can just write 0 times J. So we have only X component of this vector. So similarly, we can do this for charge Q2, but keep in mind that it's negative charge, and we know that electric field vector is always oriented towards the negative charge, and also aligns along the line between the charge and the point where we want to determine this electric field. So in this case, it will be aligned this way from point P towards the location, like position of second negative charge. So this we can call E2 vector. And what will be the magnitude of this vector? E2 equals KE times Q2 absolute value R2 squared. So again, let us write, give the projections of this vector E2 on different axes. So E2 vector, projection of E2 at axis X will be 0 because it's aligned perpendicularly to axis X. It will be 0 times I vector, then plus. So projection at axis Y will be actually the full length, the magnitude of this vector. So in this case, it will be Ke times Q2 absolute value divided by R2 squared times J vector. Okay, so now the last step, what we need to do in order to calculate the effective electric field vector, we need to add these vectors and find the resultant one. So this can be done like this, and this is our E vector, some effective electric field vector in point P, which is created by two charges, one positive, one negative, aligned with respect to point P as shown on our figure. So in this case, we have just simple adding of two vectors. So E vector is equal to E1 vector plus E2 vector, and this is equal. So we have X component of E1. So this will be Ke U1 absolute value divided by R1 squared times I vector plus, and we have Y component of E2. So we just keep these components with zeros. It will be Ke Q2 absolute value divided by R2 squared times J. So this is the answer. So this is the vector of resultant electric field in this point P. So with this, I think we are done. Let us go further and consider more interesting case. It's not always the case that charges are very sharply defined in their location and can be considered as just point charges. A system of charges can be considered as a system of point charges which are separated from each other. They can be distributed along some line, some surface, or some volume, depends on which conditions we deal with. And these charges can be so close to each other that mathematically it makes sense to consider not a system of separate charges, but a continuum of charges equally or not equally distributed over line, surface, or volume. So let us consider such a system and try to understand how to calculate electric field. So let's assume that we have some volume, and it is this volume has some uniform distribution of electric charge. Let's say this charge is positive. Let's maybe call this total charge. Oh, sorry, change this. Let's say the total charge accumulated at this volume is Q. So in this case, how do we work when we want, for instance, to calculate strands of like electric field vector created by this volume electrically charged in point P. So there is an approach we need to go, and this approach assumes that we divide this volume in very little volumes. So this will be delta Q1. This, for instance, will be delta Q2, and so on. We divide all this volume in these little volumes. Then we draw a line which goes, maybe relocate a bit this point. My lines are not so ideal. So which goes through this small volume with charge delta Q1. So we can pretty much consider it as a point because it's very small. And through this point P, where in some space around this body where we want to determine electric field. The same we do for the for all other volumes, small volumes, which we define in this body. And we have here some radius vector, R1 vector, R2 vector, and so on, which define the direction. Oops. I'm sorry, guys, for this. Need to answer. 1 second. Oh. Hi, guys. I'm sorry about this. We have some courier, and I got a package with samples from China. I need to pick it up, and somehow they cannot find me in this campus. Hopefully, they will come soon. So we continue. So in this case, we want to calculate electric field created in point 2 by these volumes, and we will have some E, let's call it maybe delta, to specify that this is electric field created by very small volume, delta E1, and we have delta E2, and then obviously we need to divide whole body in these small volumes, and then calculate the electric field created by each of these small volumes. Then we sum up them according to the rules these rules according to this rules for summing vectors. And we have E vector equal to resultant vector KE, sum of all volumes delta Q I Ri squared. Oh, they just arrived. Sorry, once more time. Okay, done with this. Sorry again. So obviously, if we put a limit of this volume when delta Qi approaches to 0, we can replace it with electric field equal to the Coulomb constant times integral dq dr square times r unit vector. So here we also have this unit vector. And this is the way how we define electric field created by some charged volume. If we have volume, some distribution of electric field, it's rho, then it's equal to total charge accumulated in this volume divided by volume itself. However, it could be surface, so it's sigma equals to area, equals to the total electric charge. Here we can call it volume charge, here surface charge, divided by area, and there is another lambda parameter in the case when electric charge is distributed along a straight line. Here we have Q, L divided by L. So these are parameters if we have uniform distribution of electric charge, then we have these parameters. If not, then we can use local parameters of volume and surface or linear distribution of charge to define these elementary charges, like not elementary charges, I mean the small charges d q in given position. So it will be, for instance, rho volume distribution times dv, so times the small volume which we consider in a given location. So in this case, we need to have some example how to apply this in some real cases, and let us consider a disk with some radius r, and if from this central point we have some perpendicular to the disk, let's say here we have some point P, and we want to calculate what will be the electric field vector in this point P next to the disk, which is electrically charged and with some surface density sigma. Let's say it's positive electrical charge. So in this case, let us consider some very small element of surface of this electrically charged disk, and this is located at a distance r from the center, and this surface, actually the charge of this small surface element which we consider will be dq equal to sigma times dA. So this is the area, small area, and sigma is uniform distribution of electric charge. So in this case, the sigma is a constant, and we need to define what will be this small area. So this side could be defined as r times d theta, the angle in between these two vectors from the beginning and the end of this side of the small area. And this side can be defined as dr. So that's why our small area is radius times d theta, theta in radians. So this is length, the product of radius to the angle in radians gives us length of one side, and length of the other side is dr. Okay. So now let us consider electric field which will be created by this small volume. We have this line. Along this line, it's positive, so it will be from the charge. This is our E, let's call it DE1 vector. So if we consider some system of coordinates, let's say we have x, y, projection of this vector on x-axis will be dE x1, and projection on the y-axis will be dE y1. So now let's get rid of this system of coordinates. Now let us consider a symmetric small area to the first one. Let's call this one, it's 1, this one is 2. So we can always find symmetric area for this, for any given area segment, because it's a symmetric body. So we can proceed further. This will be dE2 vector. The same, we will have projection here on axis x and projection on axis y. So dE2 x. Oh, sorry. It is dE y2. And here we can delete this and just extend, because they will sum up. So here will be dE1x plus dE2x. So what we see, that always symmetric elements, they will sum up in x direction and cancel components of electric field vector in y direction. They are in opposite direction. That's why resultant electric field vector from all small elements on this disk will sum up only in the x direction. That's why when we solve this problem, we need to consider only x component of electric field. So for this purpose, we can do these calculations. So let's see what will be the x of this first element, just one random element. It will be Ke times dq over d square. D square, this is the distance from this small segment, surface segment, to the point P where we calculate electric field. And also here we have some angle alpha, which we will use later to do calculations also. Because we need to have, so this is absolute value of electric field vector created by segment 1, but we need to multiply it by cosinus alpha in order to get projection on the axis x. And this cosinus, so d, the distance, can be calculated as here we have x coordinate from the center of the disk to point P. So this is the distance along axis x. This distance d will be square root of r squared plus x squared. Now, we also need to define what will be cosinus alpha. And this is equal to the ratio between x and d. And here we can write that will be x divided by r squared plus x squared in the power of 1 second. Okay, we defined all these components, and now let us substitute here in this equation for dEx. Values for dq is given here, d and cosinus alpha. So let's do it on the next slide. It will be dEx equals to ke sigma r d theta dr. This is for dq divided by r squared plus x squared. This is for d squared stands. And instead of cosine alpha, we have x divided by r squared times x squared power 1 second. So if we put all together, we get the final expression for dEx, which is k e sigma r d theta times dr divided by r squared plus x squared in the power of 3 seconds. Now we need to calculate the total electric field from every segment. That's why we need to integrate all over the area of the disk. And in this case, we will get Ex, like total electric field created by the disk, will be Ke times sigma times, oh, I forgot here, X. It comes from here. Yeah, if you see that I missed something, please interrupt me and let us know, because later we can make mistakes. So times x. So these guys are constants. We don't care about integral to put them under integral. So here we have d theta. What is the, yeah, someone actually mentioned about x. Thank you. But you can turn on your microphone, just tell me, because I don't have a chance to see every time the comments. So d theta, it's a angle in radians. So it changes for whole disk from 0 to 2 pi. 2 pi radians, it's 360 degrees. And then we also need to integrate from 0 to r radius, which changes like from 0 to r capital to maximum radius of the disk. It will be r times dr divided by r squared plus x squared 3 seconds. Okay, so in this case, we The first integral is very simple. Will be k e sigma x just multiply 2 pi, because we will subtract from 2 pi 0. The second one, we need to put under differential this r, and that's why it will be 1 second times integral dr squared, because derivative of r squared will be r divided by 2. That's why we have 1 second in front of the integral. Then we can add any constant here. It doesn't matter because derivative of constant will be 0. We have r squared plus x squared in the power of 3 seconds. dr. Sorry, no, we already don't have dr. D, this expression. In this case, it's a simple integral for which is tabulate, like in table of integrals, you can find it. And as a result of this integration, we can get the final expression, not final, but close to final. It will be 2 pi k e sigma x after integration and getting rid of coefficients, that is 2 and another 2 which we get in the denominator because of integral. We have r squared plus x squared in the power of 1 minus 1 second. And this will be from r to 0. So I changed the order for integral because we had minus after integration. This is simple approach to integrate this integral. You just need to go for integral dx over x in power n, and this will be equal to x in power n plus 1 divided by n plus 1, assuming that n is equal minus 3 seconds. So if you apply this equation, you will, for like this rule for integration, you will come up with this result. And substituting 0 and r instead of, like capital R instead of r in this equation, we will get final equation for the electric field in point P. Will be 2 pi k e sigma 1 minus x divided by r capital square plus x square, the power of 1 second. So this is the answer. This will be our electric field vector in axis in the point P, which is projection on axis x, and the only component, because we don't have any component of this vector in the projection on axis y. And what is interesting, now if we consider that x is much smaller than r, so this point P is located very close to the disk, in this case, we can write that this term, second term in the parentheses, x divided by r squared plus x squared, the power of 1 second, will be much smaller than unity. That's why we can cancel, like neglect with this component, and our electric field resultant will be 2 pi k e sigma. And assuming that k e is equal 1 divided by 4 pi epsilon 0, which we mentioned earlier, we can get that electric field close to the, in the proximity of the electrically charged disk, will be equal to sigma divided by 2 epsilon 0. So which is an equation which we will get in future for electric field created by infinite plane with uniformly distributed charge. So I wanted to show you this calculation step by step, specifically for some two-dimensional case, some like this, since again, it is one of the it's actually the most important task of electrostatics to calculate electric field vector created by different system of charges, in particular also by distributed charges. So you need to have this feeling of capabilities to do this for different cases. Also, please don't forget to read about electric field lines. It's quite simple chapter in the textbook, since it is also should be covered during this week. So I decided better to focus more on this example than on definition, like simple definitions of electric field lines concept. But this concept is very convenient for visualization of electric field. So please take your time, read in the textbook, and please ask your questions if you have any. Okay, if everything is clear, that's cool. Then we meet on Monday next week, and we continue with the Gaussian, the flow of electric field and energy of electric field concepts. So there's a lot of things to do in the future. Take your time to read during weekends this electric field lines concept. And if you have any questions on this topic, you strongly recommended to ask them on Monday. Other from that, I would like to thank you for attention and wish you good weekend. Take care and have a good evening. Thank you for attention. Bye, guys.